Matt Weddy is unable to give this talk, so he wanted me to go through his slides. I'll do my best. But my name is Oyake, and I just want to talk a little bit about what Matt is doing. So this talk is about estimating flight CPU utilization of algorithms in a desktop environment using Xprof. And Xprof is a tool that Matt has developed for Valgrind to do, essentially to get some performance metrics early on in the software development stage. So there are only a few slides here, but the tool is interesting. So the issues that he is concerned about are the flight algorithm development process, the challenge of generating CPU utilization estimates, his approach in developing Xprof, and some of you might be familiar with sort of the conventional Xprof tool. There's another tool, I think, in the sort of X Windows world. An example, he gives an example how Valgrind Xprof works, a critique of his current state, and a summary. So when you're developing computationally intensive code or algorithms, such as image processing or hazard avoidance, you want to have some kind of idea of the performance of your code. And so the algorithm development process is typically performed on desktop workstations, Linux workstations typically, running in basically a desktop environment using GCC or your standard tools. So typically what you do is you have your algorithm and you develop your algorithm on your desktop environment and you build your test harness. And then at some point you might transfer that code to the flight environment and re-implement the code there, essentially keeping your code in a clean C code format that would translate naturally to a flight environment. And so the development process typically starts with your algorithms and then maybe some simulation, some glue code to run this together. And the eventual algorithm code is delivered to the flight software / avionics group for integration into the real flight load. This is pretty typical. And so the model is delivered to the real-time simulation group for integration into their test environment. So early in the development process, the avionics group needs to size the flight computing resources. So you have finite resources in your flight computer. You want to basically have a measure of how many CPU cycles you intend to use, and basically understand if your algorithms are particularly inefficient in some way. So the required computer capacity can be driven by computationally intensive algorithms. So you might want to see if your algorithm is non-optimal in some way. Trades may be required, algorithm capability versus availability of cost of the computer. So Matt feels that the trade should happen prior to procurement, not during integration and test, and the domain experts should provide CPU utilization estimates prior to the flight computer procurement. So accurate estimates of CPU utilization can be hard to generate, and flight code is difficult, if not impossible, to run in isolation. Now, there are other tools that exist, such as Symix or QEMU. You also have KVM, and you have other tools like LLVM, which are interesting and could help you in that direction. So you want to get flop count estimates, perform a code analysis, and other things. And so he gives an example. Division is a more intensive than addition or multiplication. On PowerPC implementations, division requires about 16 times that of addition or subtraction or multiplication. So compiler code optimization can also distort estimates based on source code. Okay, so his approach is a header called Xprof req.h, and you basically copy that and you just include that header into your code. There's no library to link, no compiler arguments, and then you start instrumenting your code. And so you add these counter variables, which may be macros in this header, in your code. And so one is Xprof clear counter, so add Xprof instructions before your code fragments, and then an incrementer, Xprof get counter, actually just gets the counter, and then you print the results of your execution. Nominally run without estimating CPU load. That code runs without overhead, and then periodically run under Valgrind Xprof to get the CPU cycle. So he gives an example of this. And so here's an example. The objective is to estimate the clock cycles for flight codes executing in two modes. Compare double versus float, compare no optimization versus level 3 optimization, and then go through the build cycle, run each build under Valgrind Xprof, and if you're familiar with Valgrind, you pass in these arguments, and compare the results. And so he compares the results of mode 1, mode 2, and then the simulation. And you basically see on the left-hand side how Xprof is used. It's pretty simple. You just add the clear counter, and then you add your get counter, and then you basically capture your count variable at that point. So just a few lines of code. So it looks like it's designed for a lot. It's very simple. It's a very simple design. And so how Valgrind works. So Valgrind breaks code into super blocks and then instruments the code blocks when it executes. And instrumenting the code blocks, it converts the guest machine code into an intermediate representation, converts that tree IR to a flat intermediate representation, then it instruments that intermediate representation. And so that's where Xprof instrumentation is executed. So let's see, it looks like it optimizes the intermediate representation, convert the flat intermediate representation to a tree IR, convert the tree IR to host assembly code, allocate register, generate machine code. So Xprof contains a table that maps the intermediate representation instructions and operations to cycle counts. The default table can be dumped, and a user-defined table can be loaded. For each superblock, Xprof counts the instructions from entry to exit and adds a Valgrind dirty call to update the internal counter. Valgrind translates all the code down to system calls, and execution of system calls is not included in the counts. So for this tool, he's been working on it for a little bit. He feels it's promising. It's simple to use, a very cheap way to get an approximate CPU count statistics. Evaluates almost all code, only missing system calls. But the drawback is mapping intermediate representation operations to a target processor is not perfect. Calibration and tuning could help. The tool may work better for relative tuning, so it might give you an idea to reduce your CPU load by 25% or something like that. So it could give you essentially the metrics. It gives you coarse metrics essentially. Does not deal with the cache. Valgrind does have a cache grind tool. One common approach is to multiply cycle counts by a cache factor to get time. Does not capture pipelining. Does not currently work on multi-threaded code, and no guarantees of over or under bounding execution time on the target computer. For the challenge of sizing CPU capability early in the development stage for when you're developing algorithms, Valgrind Xprof shows some promise. The tool is easy to use and cheap to implement. Work remains to test, tune, and to calibrate. So Matt's been working on this for a little bit. If you go on the Valgrind mailing list, I think he submitted this. It's open source, and so you can download it and play around with it. And a lot of the feedback he's received has been from Valgrind users who tried it out and made suggestions on certain improvements that they feel he could make. So it's something that's sort of very early in the stages, sort of beta code, but it's useful for him in getting basically metrics for his algorithms and the instruments he's working on. So I think that is it. I can't really answer any questions on this, but I can tell you to go to the valgrind.org website. There's lots of mail there, that interaction between Matt and the users of his tool. And if you're working with Valgrind, you're really at a low level, and that's cool. So that's all I have to share.
Thank you for bringing us back to schedule.
Okay.